quite a while now, I've been interested in the interaction of metal oxide with surfaces and interfaces. This is a very important fundamental question in heavy analysis, as well as technologically important question in analysis. One only has to look at the industry and see how many catalysts are metal oxide-based catalysts versus metal catalysts. And also, to look at the number of papers presented at this symposium, probably there are more metal oxide papers than are metal catalyst papers at this symposium. And over the years, as looking at this problem, how to study oxide-oxide interactions and interfaces, it became clear to me that one of the best approaches was to use the technique of Raman spectroscopy. What I'd like to do today is give you an overview of what Raman spectroscopy can do and tell us about how metal oxides interact and interface. And to do this, I will look at three conventional supports compared by conventional methods of extreme wetness, aluminum, titanium, silica. Now look at various metal oxides and how they interact with these supports. Have a slide. So we'll look at three supports, aluminum, titanium, silica. We define what I mean by supporting metal oxide. We have oxide support substrate, the aluminum, titanium, silica, which I'll be talking about today, or it could be any other supports, zirconium, magnesium, calcium oxide that you've heard about. And what we'll be doing is depositing a second metal oxide by impregnation onto this oxide support. Now it turns out that two extreme situations can occur. In one extreme case, the metal oxide will not spread on the oxide support and will agglomerate, will amorphous, will three-dimensional material will crystallize if you heat it up. In the other extreme case, the metal oxide will interact with the oxide support and spread or wet that surface or a surface oxide overlayer, sometimes referred to as surface oxide phase or a monolayer, so that all maximum coverage. The reason Raman spectroscopy is a very good technique, for this kind of problem, Raman spectroscopy very rarely discriminates between two types of states of metal oxide. For example, the crystalline metal oxide Raman bands are very sharp. The surface metal oxide Raman bands are very broad and very, very weak in comparison. When we vary the amount of metal oxide in the material, when the metal oxide spreads to the surface oxide, the Raman bands shift with coverage due to lateral interactions in that surface oxide overlay. In the case when we have three-dimensional metal oxide phase, the Raman bands do not change with the amount of metal oxide we put into that material. Furthermore, when we do in situ experiments where we absorb gas molecules on these surfaces, since the gas molecules interact with this very well dispersed metal oxide phase, the Raman bands begin to shift because of the coordination of the gas phase molecules with the comically dispersed metal oxide species. In the other case, over here, when we have crystallines, when we bring in various gases, there's no change whatsoever. The gases are absorbing on the exterior only, and the bulk of the material is not being perturbed whatsoever, and so there's no change in the Raman spectrum. Furthermore, the surface metal oxide phases are extremely stable to high temperature calcinations. As long as the surface doesn't collapse completely, these oxide overlays are very stable to temperatures even in excess of 1,000 degrees centigrade. And if you have a three-dimensional amorphous crystalline material, it undergoes the normal phase transition of the crystallized to various temperatures. And so, the Raman spectroscopy technique is really ideally suited for looking at these kind of problems of surface oxides on oxide materials. And these are the oxides that we're talking about today. These are the metal oxides that we'll be depositing on the supports of aluminum, titanium, and silica. And these are all made by excipients wet in this impregnation. And the primary choice of method used to use water as a solvent, like magnesium, niobium, and titanium precursors were not water soluble, so we use alcohol instead. Before I show you the data for the support metal oxides on the three supports, I want to show you what the Raman spectra of the three oxide supports look like. The nice thing about aluminum is that this young aluminum is not Raman active whatsoever. It does not give any Raman active signal. So basically it's invisible. What this does for us is we can put as little as 0.1% of the metal oxide on this aluminum and still detect it because you do not get any aluminum signal. This is one of the advantages of Raman spectroscopy over infrared. Infrared, the aluminum absorbs the signal, blows out of the window. We cannot get into this region. And as you'll see, all oxide stretches are 1,000 wave numbers or below. So Raman, in a sense, opens up this problem for us. In the case of silica, there are some Raman active modes, but they're not particularly strong. Particularly, you have this very broad frequency around 400 to 600 wave numbers. But still, it's manageable and we can work around it and see what's going on. In the case of infrared, again, you have trouble seeing low wave numbers. You cannot see into this region with infrared, but the silica absorbs infrared signals. And in the case of titania gets very strong Raman signals, and I've compressed it here to put on the same slide. But these titanium bands are very, very intense. So we have trouble getting below 600 wave numbers with TiO2, but the region above 600 here is wide open for us, and we can monitor what's going on there. And so these are the references of the oxide supports. And now let's see what happens when we deposit various metal oxides on these supports. Here, for example, rhenium oxide, 5% rhenium, calcine 500 on this region support. I should also tell you that the aluminum is 180 meters per gram, titanium is a degree of 2.5, 55 meters per gram, and silica is still 300 meters per gram. And you can tell this also the structure. Raman also gives us the structure of these metal oxides by comparing it to a model compound. If you look at rhenium on aluminum, we have these three bands here. This is symmetric stretch, anti-symmetric stretch, and the bending mode of ReO4 species, and we have many reference compounds like or ammonium, radium, and so on, and they match up very nicely. So right below we can see that we have a surface of ReO4 species that will crystallize. The Re207 crystals are volatile and will not exist under these conditions by oxidation. Furthermore, the Raman also tells us that there are no bands here at 200 wave numbers. The presence of a band at 200 wave numbers tells us that we have bridging oxygens, that the rhenium are attached to the rhenium oxygen rhenium. So we don't have a band here, and that tells us that the ReO4 units on aluminum are isolated. So they're monomers, and nothing more. In the case of titania, I don't show you the data below here because of the strong TiO2 signals, so we essentially lose this information. However, look here in the stretching mode, now you see a doublet. And the Raman selection rule tells us that each symmetric stretch, one symmetric stretch per one type of species. The fact that we have two bands that tell us that titania, we have two distinct ReO4 units. Furthermore, when we change the rhenium loading, this band here loads up first. After it's saturated, then this other higher wave number band begins to fill in. And so we have ReO4 unit, and we have something, a second ReO4 unit that's slightly more distorted, and this band shifts to 1,000 wave numbers. And lastly, we have rhenium on silicon. And again, you have the symmetric stretch, the anti-symmetric stretch, and the bending mode for the ReO4 unit on silicon. And in this case, there are no crystallites. And rhenium is the only metal oxide you can put on other supports and never form crystallites under any conditions because the crystallites are volatile. And so you can see that the nature of the support affects the nature of which kind of rhenium we're going to have on the surface. Next I'll show you the nature of chromium oxide silicon. I'm sorry, I look at titanium and silicon. And similarly to rhenium, you have the stretching mode here and the bending mode here, characteristic of a CrO4 unit. However, look now at the 200 wave number region. You can see that the very weak band that goes a little bit more to you double the loading to about more than 10%. But the presence of that weak band here, 200 wave number, tells us that unlike rhenium, which is always present as monomers, ReO4, the chromium not only is present as a monomer, it's predominantly present as a monomer, but there's a small amount of dimers. We have a bridging oxygen connected to a monomer. Again, on titanium, we can't go into this region, but we have the signal here in the same region, like in the case of aluminum. So it looks like in the case of chromium, titanium, chromium, aluminum, the states or the structures are very similar. But look now, chromium and silica is totally different. I mean, rather than one big band here with multiple bands, we have sharps peak here at 550 wave number. Going back to our reference compound, which we have done, turns out that this is for a chromium tetramer. That there are 4 chromium lined up and all attached sharing an oxygen. That's only when you get these characteristic peaks. Furthermore, when you go to about 3% chromium oxide or above, this band starts to grow. This is out of the crystal, Cr2O3. And so, unlike the aluminum titanium supports, chromium doesn't spread very well onto the silicon. Part of it does, the first about 2.5%. When you get 3%, the band starts to grow. So you have both surface space of chromium and the crystallite. And the nature of surface space is very different on silica than it is on aluminum and titanium. This is what tungsten oxide presence of the shoulder here tells us that the tungsten oxide are not isolated and that we have WOW bonds. And we've also done some in situ X-ray absorption near spectroscopy work at Stanford Linear Accelerator. And this, for this particular sample, this 5% tungsten oxide on alumina, we find that we only have tetrahedra of tungsten oxide present in this loading. And so therefore, combining this with Raman, we know that we have both monomers and dimers. But now the dimers are very significant. This is a significant amount bridging off. On titanium, we can't go into this region down here. This is a weak TiO2 signal. There might be a trace of crystallite here. And again, you see the signal for the surface of tungsten oxide phase on titanium. So aluminum titanium quality has become the same. If you go to silica, you still see the surface phase there, tungsten coordinated to the silica surface. However, you see these very strong bands here, characteristic, and the characteristics that are of this place. And so again, when you change the supports from aluminum titanium to silica, you can crystalline on the silica support at low loading, not on aluminum titanium. Don't come this place, you can see monomer. This is for B205 now. Again, you have the stretching mode here, and this is the bending mode. Now, again, there's a shoulder here. When we go to higher loadings, this becomes a really nice doublet here. When you go to about 10%, the 10% only get there, double. But if the vanadium was a monomer, you would have no shoulder here at 200 wavelengths. Also, because of a different bond angle in the vanadium structure, you also get another band here, which is not very visible in the other oxides. These are associated with the bridging. This is the bending mode of the bridge. This is the linear stretch of the bridge. We've also done solid-state vanadium 61 NMR collaboration with Hecker and Santa Barbara in America. And the NMR shows that, again, for this loading of 5% vanadium aluminum, we only have tetrahedra. However, when we do magic hand spinning, the bands don't sharpen. What that tells us is that not only do we have one kind of real coordinate, but we have a distribution. Monomer, dimer, and trimer simultaneously coexisting on the surface here. This particular loading, 5% on aluminum. On titanium, again, you have the band for the surface of vanadium species. However, when you put 5% vanadium on silica, you can see very sharp bands. These are crystallized with B205. In fact, it's very hard to disperse vanadium on silica using conventional threads. And Ted Oyama will talk about that tomorrow. It's less than about 0.7%. When you go above 0.7%, the vanadium starts to crystallize very readily on the silicon surface. And the last thing I want to show you some data for is the niobium system. And here we have again niobium alumina, and it's stretching band. This is the bending mode here. And it looks, the fact that it shifted all the way down to 200 suggests again that the structures are not isolated, but they have bridging niobium oxygen niobium bonds. We're still doing some work right now to determine whether this is octahedrally or tetrahedrally coordinated by doing X-ray absorption near spectroscopy study. When you go to titanium, niobium is here, but it doesn't, if you just look at it, it's a little hard to tell. Ordinarily, titanium, the signal is going to drop like this. And so it's a very broad signal sitting here. When you go to higher loading, it becomes and grows and becomes higher. And we don't see any crystallized by X-ray diffraction for this particular material. It's 5% niobium oxide on titanium. So the surface space here on alumina, as well as here on titanium. When we go to silica, again, you see the bands, you have these two bands here on 600 and on 200 wavelengths. These are characteristics of NB205 crystalline. And with 1% niobium oxide on silica, you can still get only the surface phase. But when you go to 3%, both the surface phase and the crystallite are present. And as you keep loading higher, the crystallite start growing more and more. So to summarize, what I'm trying to show you here is that alumina and titanium support exhibit very strong capacities for forming molecularly dispersed surface metal oxide phases. The only time you'll get crystallite, and even independent of temperature, even with very high temperatures, as long as you're listed on a monolayer, you will not have any crystallite, unless you do some very good preparation and you can't have crystallite present. But the capacities for forming these well-dispersed layers are very, very strong, so these are reacting with the surface spectroscopy. In the case of silica, the situation is very, very different, as I tried to show you. Silica support exhibits a weak capacity for forming these molecularly dispersed surface metal oxide phases. And in these cases, you'll usually find that both the surface metal oxide as well as the crystalline metal oxide phases exist simultaneously on the surface as you load it up. Very low loading. So the metal oxide conform, which indicates what the family that's there. So both these factors are important. Thank you very much for your attention. I'm happy to answer any questions.
I have two comments to this very interesting paper. One concerns the last slide, in which you are concluding that aluminum oxide and titanium oxide are always good as support, because oxides are spreading easily over them, whereas SiO2 is not a good support. Now, this is a very relative business, because it depends on the conditions at the interface, one metal the other metal. And this can be treated in the same, within the same formalism as the wetting of a solid by liquid. With this difference that here we have wetting of solid by solid. And the behavior of titanium, for instance, will depend on whether the oxide which is supported on it conforms to the conditions of wetting or not. If it doesn't, in that case, the titanium will not be a good support. So I think that this conclusion should be amended by stating that the behavior depends on the conditions at the interface. This is the first comment.
Can I add this one for you?
Yes.
Well, I certainly agree with you. I mean, it's very clear. And this is for this particular method, which I use, was conventional stiffing wetness preparation of these catalysts. And I was trying to show, using conventional methods, just how changing the support changes the nature of the metal oxide on the surface. Okay? And I happen to have a slide for titanium as well, but unless you want to see it, on titanium silica, titanium aluminum. It doesn't spread on silica very well, but it does on aluminum.
Yes, I would even go a step further and say that in the future we will probably see, and we have seen in several cases already, that in case of amatase, for instance, you may have a good spreading on one crystal plane, whereas you won't have any spreading on the other crystal plane, because the surface free energy of different crystal planes differ, of course. My second comment concerns the application of Raman spectroscopy. I think that, as with all methods, it gives you a partial answer, and it would be extremely dangerous to base only on Raman evidence to draw full conclusions about the state of the oxide at the surface. Because we know that, for instance, certain vibrations have almost the same value in many different compounds. Take the stretching vibration of molybdenum-oxygen bond, whereas these compounds behave in a completely different way in the chemical reaction. Therefore, you may have the case that at the surface you observe, in two cases, very similar vibrations in your Raman spectrum, but these two oxides have different behavior in the reaction, because the influence of the support makes them influences the reactivity to a different degree.
I agree with you again. First of all, the substrate has found that when the metal oxide bond strength input structures were the same. For example, in chromium, titanium, chromium, aluminum, the Raman looks the same. Because as soon as you heat it up, the chromium on titanium decomposes to chromium-3, whereas chromium on aluminum stays at chromium-6 to 1,000 degrees or above. So it does not give some sense of chemical information, which the substrates are doing. Also, we don't rely totally on Raman, although my confidence in Raman is very strong, because we have done solid state NMR experiments and in situ X-ray absorption near X-ray spectroscopy to back up our experiments, like in the case of rhenium and tungsten and vanadium. So we have additional information from the other spectroscopies that complete the picture and give us more confidence that the Raman is telling us the right answer.
Just if we comment on the also, so in private to this comment, I'm the first speaker is Professor Kuhn.
I will come to one question university. It's a comment and then a question. In the data that you reported as well as those in the literature, the vibrational peaks in the spectrum that are associated to certain species are usually very broad compared to the crystalline materials as well as the corresponding species in solution. It seems to me that this suggests that the metal-oxygen bonds, such as the bond length and the bond angle of the species on the surface, are quite perturbed, I should say, compared to those species in solution. Well, that's not unreasonable, for example, because this surface species has to be supported on the support, so that the bonds has to conform to the structure of the substrate as well. Now, in many of the species that you propose, such as M04 and M07 species, they are formally charged. They carry a negative charge. And in solution, these charged species will be stabilized by the absorption by these solid molecules as well as by counter ions. On the surface, the charge has to be balanced as well as stabilized as well. There are several ways you can do that. For example, some of these oxygens in the species are not totally associated with the surface species. They are shared with the support, so that we're talking about actually an MO support bridging bond rather than just an MO4 isolated species. There are other possibilities, such as, for example, the species of the surface species not actually sitting on the surface. They may be partially submerged. Maybe 2 sides or 3 sides of the crystal is actually in the solid. This way, the solid would act as a solvent and stabilize the charged species. Furthermore, you can also protonate this surface species. So all of this could contribute to the distortion of the surface species and causing this broadness of the peaks. I guess I'm asking you then, what is the view of this picture that I just proposed, and how do you think that the surface species charge is balanced?
A 5-part question. We'll start at the beginning. First, why are these metal oxides in storage? And the reason is that the metal in the water, aqueous medium, or in a solid, like in scheelite structure, all the metal oxides experience the same environment in the bottom and underneath. So they seem to go in the z direction. The same environment is experienced this way, and the same down towards the surface. And there are many such cases. We've done many recent experiments with John Thomas. We've looked at bismuth molybdates, bismuth vanidates, tungstates, bismuth niobius, and bismuth tantalate. And what we find there is that these materials have essentially monolayers of these metal oxides that's sandwiched by bismuth, and they look just like in solution, perfect tetrahedron when they are tetrahedron. Occasionally they're octahedron as well. However, when you come down to the surface now, the surface is only towards, only down. You have nothing in the z direction away from the surface. You have unequal environment. And the metal oxide is responding not to the structure of the surface, the distortion of the structure of the surface itself, but the fact that it has to terminate that function. It can either terminate by OHs or it can terminate by double bonds. And it appears most of the metal oxides we have studied, and Raman shows us very clearly, because it's very sensitive to double bonds, the metal oxygen double bond thread, that these metal oxides at the surface choose to terminate with double bonds. And so therefore they will be distorted relative to their aqueous or bulk counterparts when it's perfect tetrahedron. The second part of your question is regarding broadening. There are several reasons for broadening. One is that in the case of aluminum, the surface is not totally uniform. In fact, we see this if we heat up aluminum to high temperatures like 1,000 degrees and then put these metal oxides on, you get much sharper Raman bands. And so in a sense, it's sort of crystallizing the aluminum surface at higher temperatures. That's partially the reason. Another reason is that we've seen that not only one metal oxide species is used. In the case of rhenium, rhenium is the only species that have ReO4 monomers. It's only ReO4 present under these conditions. And when you go to other metal oxides, you always have 2, 3, or 4, or many more possible species simultaneously present. And these lead to broadening of the band as well. But it turns out that the most important reason is the third reason for this broadening, and this is the presence of absorbed water. And all this Raman spectra I showed you today were ambient. Water was present. And about 4 years ago, I published a paper with Keith Hall entitled In situ Raman spectroscopy that supported metal oxide. And in this paper, when you heat up these samples and let the water desorb, the band sharpened dramatically.